Compactness is a topological property. Compactness is a topological property. So it is preserved. A topological property is preserved under homeomorphism. Yeah. So if you say that something is a topological property, then it is preserved under homeomorphism. What does that mean? If you're having this map as a homeomorphism, then if x is compact, then y should be compact. Also, if y is compact, then x should be compact. So we are going to let this be a homeomorphism. Let it be a homeomorphism from topological space X to topological space Y. And let what? We shall consider what? Let y let me consider x. Let x be a compact space. Let x be a compact space. So we show that y is compact. You can as well let y. I'm going to do this as a two-sided proof, because I said that for a property to be preserved under homeomorphism, if you suppose that this is compact, then you show that this is compact. Also, if you suppose that y is compact, you show that x is compact. So I'm going to do both cases. So what is a homeomorphism? You have to understand that a homeomorphism maps. Maps. It maps open sets to open sets. It maps open sets to open sets. Then, if we say that this is a homeomorphism, that implies that f is 1 to 1, f is onto, f is continuous, and its pre-image, f inverse, is also continuous. That is a homeomorphism. It maps open sets to open sets. F is continuous. Onto is what? It's a bijective map. 1 to 1 and onto is a bijective map, continuous map, and the pre-image f inverse is also a continuous map. It's also a continuous map. So you need that as a preamble to this interesting proof. Having taken note of that, so we have supposed that x is compact. We want to show that y is compact. So we follow the same basics. If you want to show that a space is compact, you suppose an arbitrary open cover of that space. Then you show that that arbitrary open cover has a finite subcover. So let this be an arbitrary open cover of y. Let it be an arbitrary open cover of y. So this is consisting of open sets. U is open. It is consisting of open sets in y, U such that U is open in y. And that collection, the union of that collection is the whole of y. Yeah, it's the whole of y, the union of this collection. So a homeomorphism is a continuous map. It's a continuous map. So we have this collection consisting of open sets, implying that since f is continuous, since f is continuous. In the previous video, I've explained what a continuous function is. Since f is continuous, comma, then gamma whereby u is open, y gamma is an open cover. Gamma is an open cover of what? Gamma is an open cover of x. Is an open cover of x by sets open in x. By sets open in x. Since x is compact, comma, then it has a finite subcover. It has a finite subcover. Let this finite subcover be, let this be f. Let this be collection beta for image u1 u2 up to uk. Now consider the ui's. Consider the ui's which correspond to each inverse function. Consider the ui's. Consider the ui's, the u1s, u2 up to uk. Consider the ui's that correspond to each. Consider the ui's that correspond to each of the f inverse ui. Consider the ui's that correspond to each f inverse ui. Then those ui's, the ui's u1, u2 up to uk form a finite subcover. They form a finite subcover of what? They form a finite subcover of y. They form a finite subcover of y. So implying that y is compact. That is the first part of the proof. Now what if, suppose that, because in the first value we suppose that x is compact. Now suppose that y is compact. Suppose that y is compact. We show that x is compact. We show that x is compact. We show that x is compact. Remember, for a homeomorphism, f is a homeomorphism. F is continuous, and its inverse function is also a continuous map. Its inverse function is also a continuous map. So we want to show that x is compact. We are going to let we are going to form an arbitrary open cover of x, show that it has a finite subcover. Let gamma be an arbitrary open. Let's be an arbitrary open cover of x by sets open in x. Let be an arbitrary open cover of x by sets open in x, What next? What next? If we have that, we have an arbitrarily open cover of X by sets open in X. What next? What next? Be an arbitrarily open cover of X by sets open in X. So gamma, a collection of U such that U is open in X. U such that U is open in X. What do we observe under this scenario? We have a map taking X to Y. Now this Y is compact. Y is compact. Y is compact. Also, the inverse mapping is continuous. Also, this is continuous. So I have let gamma to be an arbitrarily open cover of X. So this X is being covered by something. Sets open in X. It's being covered by sets which are open in X. The U's which are open in X. The U's which are open in X. So what do we observe about those U's? Since F is continuous, I told you that a map is continuous. A map from X to Y. This map is continuous if for each open set in the image, for each open set U in here, for each open set U in here, the inverse of U is an open set in X. The inverse of U is an open set in X. Now, I have suppose that Y is compact. I have open sets here which are covering X. Open sets which are covering X, and this F inverse is continuous. Remember, this map is continuous. F is continuous. If you pick an open set in the image, the inverse of that open set is also open in the object. So we have this. Now F inverse, the object of F inverse is actually Y. The object of F inverse is Y, and the object of F inverse is Y, and the image is X. So that means for each open set in X, in the image, the inverse which is actually F, the inverse of F inverse, which is actually F, should be open for each U here. FU should be open. FU should be open in Y, since F inverse is a continuous map. So since F inverse is a continuous map, then beta consisting of F U open in U open where? So U is open in X forms an open. It forms an open cover of Y. Forms an open cover of Y by sets open in Y. What next? By sets open in Y. Now, since Y is compact, comma, there exists a finite subcover. There exists a finite subcover f u1, f u2 up to f uk. There exists a finite subcover this from beta, which covers y. So if you have that finite subcover covering y, then u1, u2, uk forms a finite subcover, finite subcover of x, finite subcover of x by sets open in x. So this implies that x is compact. So compactness is preserved under homeomorphism, hence a topological property.